This video is about making a so-called lie detector. You will construct it with your own hands, soldering on components like transistors, resistors, a capacitor, and so on. This electronic project puts out an audio signal that tells how good a conductor something is. You can even create circuits out of bodies and determine how good a conductor our bodies are. When our skin becomes wet, we become better conductors of electricity. That's the tie-in with so-called lie detector. In real polygraph tests, they actually measure how wet a person's skin gets because of perspiration. In other words, when people become scared, their hands sweat, and that can be precisely measured. On your lie detector, you can sort of cheat by grabbing it harder or softer, unless you put some kind of a device on the end to even out that pressure. There's a good video that you'll watch that will explain more about polygraph tests. Don't be intimidated by this project. Although it's a big project, we will take it one small step at a time. You will successfully complete this project, and furthermore, you can take it home, show it to your friends and family, and keep it. Let's get started. This piece of paper is going to be your roadmap as you construct the project. Get a pair of scissors and cut out this square part. This is the pattern for making the circuit board. Ask your instructor for some clear plastic. This is what will make the base of the circuit board from. Cut the plastic so the plastic is a little bit bigger than the paper pattern on at least two sides. Having the plastic a little bigger than the paper pattern allows us to tape on the pattern to the plastic. Do it, taping in at least two places. Notice that the print side of the pattern faces the plastic, so you can see the pattern through the plastic. Cut out the pattern, cut a piece of clear plastic a little bigger, and tape the pattern onto the plastic so the pattern shows through. Pause the video here. Next, we're going to scratch or scuff up the plastic with some sandpaper. We do this so that some goop that we're going to put on there will stick better. Plastic is very smooth, but the scratches will give the glue something to grab onto, so the glue is less likely to peel off. Scuff up the plastic over the paper pattern, but don't use the sandpaper so much that you tear holes in the plastic. Get a permanent marker and write your initials on one of the corners of the plastic so your project doesn't get mixed up with somebody else's. Sand the plastic that's over the paper, put your initials on a corner of the plastic, and pause the video here. Later on in this project, we're going to be soldering, and unfortunately, the clear plastic we're using can melt. We need to put down a thin, fairly clear barrier that can take the heat, and that's going to be silicone. Silicone is amazing stuff. It's messy to put on, but once it's dry, it's stretchy, heat-proof, waterproof, really useful for a lot of different projects. In the next step, we're going to coat the plastic with a thin coat of silicone sealant. Ask your instructor to squeeze out some silicone. If you do it yourself, make sure that when you're done, you release the pressure on the silicone so it doesn't keep coming out. Do this by pressing on the button at the back of the dispenser. And if you know the silicone will not be used for a while, stick the nail back in so it will not dry out. Ask your instructor for a piece of cardboard to use as a spreader for the silicone, and spread it and turn it, and then spread some more and turn it, and spread some more and turn it. You only have to cover the plastic that's over the paper. Cover it with a thin, even layer of silicone. When you're finished, throw away the cardboard. Put the project in the storage space so it can dry. Ask your instructor to dispense silicone onto your plastic. Use cardboard to spread it into a thin, even layer over the paper pattern. Ask your instructor for some 22 gauge wire. You'll be covering the lines with the 22 gauge wire. It's 8 pieces, each 2 inches long. 2 times 8 is 16, so you'll need 16 linear inches of the wire. Cut off all the wire you'll need at once, so you're not hogging the spool. And give yourself a little bit of extra. Make it 17 inches of wire that you cut off, not 16. Now cut the wire into 8 2-inch pieces. Copper, as metals go, is actually pretty soft, and you can cut copper wire with scissors when it's this thin. Cut off 17 inches of 22 gauge wire, then cut 8 pieces from it, each piece 2 inches long. There are lots of ways to get the insulation off the copper wire. These are a common kind of wire stripper. When you clamp on a piece of wire at one of these half holes, they cut through the insulation, but they don't actually cut through the copper wire. So grab one end of a piece of wire with a pair of pliers, and about at the halfway point, clamp onto the wire in the smallest hole. By the way, wire thickness is measured in gauge, and the funny thing is that the higher the number, the smaller the wire. So 22 gauge wire is actually much thinner than, say, 10 gauge wire. This kind of wire stripper is very common, so get to know how to use it. Grab the wire with a pair of pliers and close the strippers on the wire about halfway. With this kind of tool, it can be a good idea to twist it a little bit so that it actually grabs into the insulation. Otherwise, it may slide off. Then flip around the wire so you're grabbing onto the bare copper part with the pliers, and just pull the rest of the insulation off. Here's a really cool kind of wire stripper. The top of it is just a wire cutter, but the bottom of it, if you put it on the insulation like this and squeeze the handle, watch what happens. And here's another automatic wire stripper. If you look at the holes here, you see how it gets smaller and smaller and smaller, and yet the smallest one is all the way over here. Just put it in and squeeze the handle, and you're in business. Whichever of the wire strippers you use, you still have to grab the half-stripped wire with a pair of pliers and yank the rest of the insulation off. When you're done, you should have 8 bare copper wires. And just throw the insulation away. Strip the insulation off of all 8 pieces of wire. In this next step, we're going to straighten out the wires. Now, they don't have to be perfectly straight, but they have to be pretty straight. If you look at these wires, you can see little kinks and bends, but overall, they're pretty straight. I wish I could tell you a fast, easy way to straighten all the wires, but I don't know of a shortcut. All I do is grab it with a pair of pliers and work it one bend at a time. And then I go over it again and again until I get it straight. Experiment and find out what works best for you. Take your time and do a good job. Please do not come to me and say that you cannot straighten out the wires. It's a new skill. It's going to be hard. Keep with it until you get it to work. Straighten all 8 pieces of wire. Ask your instructor to check them when you're done. When you finish with the next step, this is what it's going to look like, just so you know what's coming. Once again, ask me to dispense the silicone, or if you do it yourself, it has to go in 2 lines in very specific places. Notice that the lines of silicone go over the ends of the lines of the pattern. Then pick up the straightened wires and push them in. I like to do it with the pair of needle nose pliers, but you decide what works for you. In any case, make sure you push them in exactly over the pattern lines. And make sure that the ends of the wires are well pushed in to the silicone, so they'll stay there when the silicone dries. If you're not sure that the wires will stay in, get a scrap of something and kind of dab it around to make sure that the silicone closes over the tops of the wires. Ask your instructor to dispense 2 lines of silicone. Push the ends of the copper wires into the silicone. The silicone used in the last step to glue in the wires has to dry, or at least skin over, for about 15 minutes. So let's do some other stuff. These are the remaining components that you'll add to your lie detector. 2 resistors, 2 transistors, a capacitor, a 9-volt battery clip, and a speaker. These black things with 3 legs are called transistors. But what does a transistor do? Basically, they use a very small amount of electricity to trigger a much larger amount of electricity. This might sound kind of strange, but a transistor is to electricity what a throttle is to a 4-wheeler. Pushing the throttle with your thumb hardly takes any energy. But because it releases gas into the engine, it releases a huge amount of energy. Who would have thought that a thumb could be so powerful? Well, transistors are the same way. They use a small amount of electricity to trigger a much larger amount of electricity. The transistors are the first thing we're going to put in, but right now the wires are too close together. We have to spread them out to match 3 copper wires like this. When you're done, it'll sort of look like a pitchfork. So first we bend the outside wires to about a 45-degree angle. Then we bend the transistor wires again in the middle of each wire so that the ends of the wires are pointed in the direction that they were originally going. You should have about as much space in between the transistor wires as is between the copper wires. Do the same thing to the other transistor. Spread out the outside wires of the transistors, then bend them in the middle to look like pitchforks. Go check your project. See if the silicone has dried enough, or at least skinned over enough, that it won't make a mess. If so, peel off the pattern and all the tape. And make sure you throw them away. Notice that your project has a copper side and a plastic side. Next, we're going to be numbering the copper wires, and notice that the numbering is on the plastic side, not on the copper side. It doesn't matter which is the top, but once you start writing numbers, that becomes the top. Start it to your left with number 1 and work your way over. Make sure that each number exactly corresponds to a copper wire. On the plastic side of the project, number on the top from 1 to 8. Look at your wiring diagram and think of it as kind of a roadmap. Look at your transistors and notice that they are placed in the middle of the circuit board, not way up by the numbers and not way toward the other side, but right smack in the middle. Also notice that both of the transistors have a flat side and a curved side. The flat side faces toward us, away from the numbers. Notice that the transistor on the left has the numbers 3906 on it. And notice that the legs, the wires of the transistor, go into the wires 2, 3, and 4. And then notice that the transistor marked 3904 has wires that go into 5, 6, and 7. Put your project down with the numbers on top, just like the roadmap, and put dots right in the middle of the circuit board at wires 2, 3, and 4, 5, 6, and 7. We're going to punch through the soft circuit board where the dots are. There are several different things you can use. A thumbtack, a toothpick, a paperclip, they all work. Make sure that the holes you punch are right above the wires underneath the plastic. Whatever you're punching with should actually hit the wire once it goes through the plastic. Punch 6 holes for transistors 2904 and 2906 in the middle of wires 2, 3, 4, 5, 6, and 7. It's time to put in the 3906 transistor. When you look at the flat face of the transistor and get the light just the right way, that's when you can read it. Grab it and put it in the pre-punched holes. It can be a little bit tricky getting it in. Make sure the transistor wires go to 2, 3, and 4, and make sure that the rounded side of the transistor faces the permanent marker numbers. If you have trouble getting one of the legs of the transistor in, like I am here, it might help to grab the leg with a pair of needle nose pliers and push it through. Now find the 3904 transistor and put it in at 5, 6, and 7. Once again, the flat side must face away from the permanent marker numbers. Push the transistors into the circuit board. Make sure that the round sides face the numbers you drew. When you plug in the soldering iron, it takes about 5 minutes to heat up. Remember that it's not just the tip that can burn you. This entire part of the soldering iron can burn you. Only the handle is safe to hold on to. Although the chances of getting nailed in the eye with a hot soldering tip are small, if it happened, the results would be catastrophic. The pain would be indescribable, and it would result in permanent loss of vision in that eye. So wear safety glasses. Remember that solder contains lead, and lead is poisonous. Even though with thin solder you can actually break it off with your hands, after you finish using solder and handling it, wash your hands with soap and water. Any device that's plugged into the wall can give you a shock if something goes wrong, and the soldering iron's no exception. Actually, it's the cord leading to the soldering iron that I'm concerned about. I know this sounds crazy, but people concentrate so hard on soldering whatever has to be soldered that they might not notice that the cord is getting too close to the hot part of the soldering iron. So inspect the cord before you start using the soldering iron. And if you find something like this, unplug the cord from the wall and tell your instructor. What we'll do is wrap up that bad part of the cord with some electrical tape. If the sponge is dry at your soldering station, wet it now. Remember that it's there to wipe the crud off of your soldering iron tip. But if you overdo it, you'll cool down the tip so much that it won't be much good for soldering. Before you start soldering, make sure that the wires that are going to be soldered actually touch each other. You're making your job much harder if they don't. In this case, there's two wires that don't touch, and I'm using a toothpick to kind of push the one wire against the other wire so that they do touch. And if you find that the circuit board moves around annoyingly when you try to solder, just tape it down. Here's some slow motion clips of soldering. Notice that we add a little bit of solder, just enough to connect the two wires being soldered, then pull the solder away. But keep the soldering iron on the connection another second or so and rub. Sometimes if the solder blob doesn't make the right connection, rubbing it a little bit with the tip can make it stick where it didn't before. Look at this solder connection. We tried to solder it, but it didn't work. Let's have another go at it. By the way, the smoke is the flux in the solder, and that helps the solder stick better. If it's taking you longer than 5 seconds or so to make a solder connection, something's wrong. Talk to your instructor and get a demonstration, or review the video again and see what you're doing wrong. It's not good enough for the solder connections just to look like they're connected. You actually have to test them. And to test them, I use what's called the wiggle test. I grab the transistor and wiggle it, but I look at it on the other side where the wires are. Can you see the wire that's not connected and is revealing itself in the wiggle test? Let's look at it again. This one here is clearly not connected. It happens to everybody. Just go back and resolder it. So go ahead and solder in all 6 transistor wires. Then ask your instructor to inspect your solder connections. Solder in your transistors, then ask your instructor to inspect the connections. We're going to be soldering in resistors next. Notice that the colors are different on the resistors, so there are 2 different resistors. But let's take a minute to try to understand what resistors do. Basically, they resist electricity, kind of like the defense of a football team. Check out this football scrimmage. This is the offense. They're trying to move the ball forward. In electrical terms, we could say that they have voltage. These guys over here are the defense, and they're trying to stop the ball from moving forward. In electrical terms, we would say that they have ohms, because ohms is the measure of resistance to electricity flowing.
That's the way, Dyra!
Let's go back to the colors on the resistors. The colors represent numbers. The higher the number, the more resistance, in other words, the more defense against electricity there is. This piece of paper will help us decipher the color code. If you do a search on the internet, resistor color code, it's easy to find. When you're going to read the colors on a resistor, always put the gold band on the right-hand side. Theoretically, this is supposed to tell you the tolerance of the resistor. That is, how good a quality resistor it is. But honestly, nowadays the quality of resistors is so high that I've never seen any color other than gold. So I just put it always on the right, and that tells me what order to read the colors in. In this case, gray, red, and orange. The number that goes with gray, the first color, is 8. The number that goes with red, the second color, is 2. After 2 colors and numbers, it almost seems too easy. And wouldn't you know it, they're going to throw you a curve now for the third one. The number that goes with orange, the third color, is 3. But we're not going to write 823. The third color tells you how many zeros to add to the first 2 numbers. So the total number is 82,000. K is short for kilo, which means 1,000. So we often say 82K instead of 82,000. And remember that ohms is the measure of electrical resistance. So we would say 82K ohms, and the symbol for ohms is sort of an upside-down horseshoe. By the way, you know that kilo in front of a word means 1,000. But what's the prefix for a million? The answer is mega. And what's the prefix for a billion? The answer is giga. And what's the prefix for a trillion? The answer is tera. Although we've been talking about electricity, you'll probably hear these prefixes again when talking about computer memory. Here's the 82K resistor. It's off over by the numbers, and it goes into wires 1 and 3. Although you're marking the dots near the numbers, don't mark them right over the big glob of silicone. Remember those big globs of silicone that we put on earlier? Because remember, the copper wires are buried in the silicone, and it would be very difficult to make a solder connection there. So put the dots down here, not up here. So punch the holes just as you did for the transistors, except this time you're going into 1 and 3. And kind of bend the wires so it forms like a U shape. And push it in. Make sure it's the 82K resistor, because your project won't work if you have the other resistor in there. Now pick up that other resistor, and if you have the gold band on the right, as you should, it reads yellow, violet, and red. So let's break the code. Yellow is 4, violet is 7, and red is 2, which means we put 2 zeros at the end. So we can shorten 4,700 or 4,700 to 4.7K ohms. Once again, bend it into a U shape. The roadmap says it goes in wires 6 and 8. So mark it if that's helpful to you, and punch wires 6 and 8. Once you've determined which resistor it is, it doesn't really matter which way you put it in, but do push it all the way in so that the resistor is up against the circuit board. Using your roadmap, determine where the resistors go and put them into the circuit board. Go ahead and solder in those two resistors. And don't forget the wiggle test. All these wires sticking out are getting to be a problem. For one thing, they will start to get in the way as we try to get in and solder other stuff. Even more importantly, if one of those wires bends over and touches another wire, electricity will go where it should not go. And once the battery's attached, it could not only make your project not work, but you could actually destroy your project. Fortunately, the remedy is simple. We'll just cut them off. Although needle nose pliers do have a cutting part, because it's in the middle, you can't cut very close with needle nose pliers. Instead, use these special cutting pliers and cut with the tip. Notice how short we can cut them, and that's what we want, short. Cut all the resistor wires and cut all the transistor wires too. Wear protective eyewear here because the wires shoot out at high speed and they could really do some damage to your eyes. Solder in both the resistors. Do the wiggle test and cut all the wires that are sticking out of the bottom. Protect your eyes. The next component we're going to put in is called a capacitor. It can absorb and release small amounts of electricity very quickly, kind of like a rechargeable battery, except much, much faster. The capacitor is responsible for the pulses of electricity sent to the speaker that, when all put together, kind of sound like a musical pitch. The capacitor's lead wires go into 4 and 8. The roadmap shows that the capacitor fits in between the resistors and the transistors. Mark the holes if you wish. Punch them. And put the capacitor in, pushing it down so it's close to the board. Electronics people say that the capacitor is unpolarized, which means it doesn't matter which way you put it in. The resistors were also unpolarized. It didn't matter which way you put those in. However, the transistors, remember those? You had to put them in a certain way. We say that the transistors were polarized. Solder in the capacitor. Cut 3 more wires, each wire about 2 inches long. This time, you're not going to strip off all the insulation. You're only going to strip off a little bit on each end. Cut 3 pieces of wire, each about 2 inches long. Strip off about 1/4 inch of insulation on all the ends. This is the speaker you're going to be using. Handle it carefully. That black stuff is really just thick paper, and it's not hard to wreck it with your finger or something. We're going to work on the other side. There are 2 solder tabs, which we're going to solder to 2 of the wires you just cut. Put the end of one of the wires through one of the holes of one of the tabs. It's pretty easy to solder unless you get the broad side of the soldering iron near the magnet in the speaker. Do that and it'll tend to grab, but if the tip of the soldering iron faces the magnet, it's not so bad. Your speaker may have a minus and a plus sign at the solder tabs. For this particular project, the plus and minus sign do not affect where you solder the speaker in. However, in some other projects, it might. Notice that on the roadmap, the leads from the speaker go into wires 4 and 5. You know the routine by now. I have to warn you that it's a little bit hard to get the wires to stay in place because the heavy speaker wants to drag them out. You might want to put on a little masking tape or something to hold them in, or you might not need it. Use your judgment. Solder 2 wires onto the speaker's solder tabs, then solder the other ends of the wires to 4 and 5. You should have one short wire left, and that's going to be a jumper, which you can see right here. The jumper's function is to jump electricity from wire 3 to wire 7. Go ahead and do what you have to do to solder that jumper wire in. Solder a jumper wire from 3 to 7. The next thing we're going to solder in is the battery clip. Do not actually hook up a battery to your project until your instructor has had a chance to inspect your project. If something wasn't put in right, or if some wires cross, not only would your project not work, but you could actually destroy it. There's a color code at work here. Black means negative and red means positive, and it does matter which goes where. In other words, this is a polarized connection. The roadmap shows that the red wire is going to go in 2 and the black wire will go in 5. This wire is kind of thin and it can be hard to get it through. It also tends to pull out very easily. So once again, you might want to tape it or not. Use your judgment. Solder the red wire in 2 and the black wire in 5. The last thing to solder in is the 2 touch wires. They are each about 6 inches long. This time on one end of the wire, you'll want to strip off quite a bit of insulation, maybe an inch or so that you have something to grab onto. But on the other end that you'll solder in, just take off a little bit of insulation. The roadmap says that the wires go in 1 and 8. Cut, strip, and solder in the touch wires. It's time to test your project, and you'll do that with your instructor. Before you bring your project to your instructor, double check with the roadmap and make sure that every component is where it should be. Then, do the wiggle test on your components and make sure they're actually soldered in. Check your work using the roadmap and the wiggle test. Then tell your instructor that you're ready for the power test.